Ever wonder what clay is made of? I'm guessing if you click this video, the answer is yes. Well, as advertised, that is exactly what I'll be talking about. And as we can see in this picture already, there is some pretty cool structures of clay minerals out there. So let's talk about what clay is made of, what controls the composition of the clay that forms, and some of the different types of common clay minerals. So first, let me recap the first clay video I did talking about what clay is, how clay forms, and where clay accumulates. So just to kind of summarize that video, which I'll link up to the top right if you want to check it out in full. Basically, clays typically form in soil, and typically the less weathering or rain you have, the thinner the soil, but the more soluble minerals present. So less clays, because clays are more insoluble secondary products rather than the soluble primary or initial minerals present before the weathering. And then once you have a lot of weathering, because that's how clays form, you get a lot more clay formation or secondary phase formation, and therefore thicker soils. But these soils are nutrient poor because the nutrients and soluble minerals are carried away with the rain. And then we talked about how rain dissolves minerals, because the whole process of clay formation is that rain comes and dissolves the primary or the original mineral, and therefore the ions that are then left over create secondary phases called clays, which are a little bit more resistant to weathering after the fact. And this is because rain is acidic. That's how it initially dissolves the original minerals, and that's because it reacts with carbon dioxide and sulfur dioxide in the atmosphere to form sulfuric and carbonic acid that dissolve rocks. And the type of secondary phase that forms after this dissolution process, aka the type of clay mineral that forms, is dependent on the composition of the primary mineral, or the original mineral that becomes altered and dissolved. And that composition can either be felsic or mafic. The meaning of felsic and mafic, these are igneous terms. It just means whether it has more or less silica or silicon dioxide. The more silica it has, it's felsic. The less silica it has, it's mafic. That doesn't really matter for the purposes of clay formation. What matters is actually the ion, the cation composition of the mineral. So for example, a felsic mineral like feldspar has cations that can form secondary phases, including potassium, sodium, calcium, stuff like that. Whereas mafic minerals tend to have denser cations like iron and magnesium that then go on to form the secondary clay mineral. The other thing that controls the type of clay that forms, or secondary phase that forms, is the ions at the mineral solution interface, so where the rainwater meets the rock and alters it. And the last thing is temperature and amount of water through flow, which are obviously, these factors control any chemical reactions, so that makes sense. So what types of clay form from what types of primary mineral? So if we look at the felsic example of feldspar minerals, these typically form kaolinite clays, which is just kind of aluminum silica, kind of very similar to the feldspar composition, honestly, just, obviously a different size grain and a secondary precipitation. Remember, we talked in the first clay video about how clay is literally just a size term. However, that being said, there are different types and compositions of clays that are commonly formed due to sedimentary processes. And so these are defined by composition. The term kaolinite refers to clay-sized things that are composed of aluminum silicate. And then we have clay minerals or secondary phases that form from more, felsic to mafic, the whole kind of range of minerals, including biotite, pyroxene, and amphiboles, which form chlorite, illite, and smectite clays. So these are very similar to kaolinite, but they contain a bit more calcium, sodium, potassium, iron, magnesium, all of those things, depending on, again, the initial mineral. If it's more mafic, you'll probably have more iron and magnesium. If it's more felsic, you'll get more sodium, potassium. If it's intermediate between the two, maybe you'll get calcium. And then your ultramafic or very silica poor igneous mineral olivine, which is a ferromagnesian or iron magnesium silicate mineral, that forms serpentine due to alteration. Now, serpentine is not technically a clay mineral, but it is a secondary phase from the alteration of a primary mineral, in this case olivine. So it's important to remember that not all secondary phases due to alteration or weathering are defined as clay minerals. But for the most part, the chlorite, illite, smectite, and kaolinite groups are defined as clay minerals. Now, because mafic minerals are not as common in the upper crust, especially the continental crust, typically in soils, we don't get so many mafic secondary products or secondary products from mafic minerals. We tend to get, more so feldspar alteration products, such as kaolinite. That's why it's so common. But we still do get these other products occasionally. They're just maybe not quite as common, especially in continental crust, because again, remember, oceanic crust is where we have basaltic or mafic minerals, but the majority of continental crust is more felsic. So that's why those are slightly less common. But these ferromagnesian-rich minerals weather very rapidly in oxic environments or, environments where there's oxygen, like anything interacting with the atmosphere. So if these minerals do make it to continental crust and they are exposed to the atmosphere in an oxygenated setting, they will weather very rapidly to become these secondary products. And because mafic minerals also contain the majority of transition metals on Earth, they are also great targets for organisms, microbes and other, fungi and stuff. They love to attack mafic minerals to get transition metals from them because transition metals are important micronutrients for these organisms, including us. We also need transition metals, but we get them from the things we eat because they attack these rocks and they get them from the rocks. For example, iron is really important for us as well as them, so they have to get the iron somehow. So a lot of fungi and microbes will produce organic acids that dissolve or help to dissolve mafic rocks and minerals so that they can get the ions that they want from that mineral. So that kind of biological component also speeds up the rate of mafic mineral dissolution. So now we'll get to the structures and bonding in clays. I won't get too deep because I'm not a clay mineralogist, but I'll talk about the general layout of a clay mineral in terms of its atomic arrangement. And then we'll talk about the classification of different types of common clays, like I just mentioned in the previous slide, and I'll show their chemical formulas and all of that. So, clay minerals, they're typically what we call phyllosilicates. I called them in the previous clay video aluminosilicates because they contain aluminum and silica, but remember, that's using terminology that defines them based on their composition, so they're aluminum and silica rich, but we can also define them in terms of their structure. So they are silicates, but phyllo means that they're layered silicates. So this is kind of their structural definition because they have layers, and two major types of layers exist in phyllosilicate clay minerals. These are the tetrahedral layers, which are typically silica tetrahedra, which are basically, you have a silicon atom in the center and then 4 oxygen atoms in a tetrahedral shape, and that makes up these units, these tetrahedra units that form a sheet in the clay mineral. And then the other thing that can be in the center of the 4 oxygen atoms for the tetrahedra is aluminum, but typically it's silicon. And then the other type of layer is octahedral layers that form and kind of are interbedded between the tetrahedral silica layers. And these octahedra can have various different cations, including aluminum, iron, and/or magnesium. And then there's even things called interlayers in between the tetrahedral and octahedral sheets, where you might just have a layer of pure cations, like, for example, potassium sometimes fills the interlayers if there's a negative charge that needs to be balanced out in the interlayer, or sometimes that's filled with water, which is why clays like to cling onto water really easily and are hydrous, or they form hydrous forms as well. But, it kind of depends on the structure, the charge, and the clay mineral that you're talking about for what fills the interlayer and if there's an interlayer present to begin with. In any case, the tetrahedral and octahedral layers are held together by shared oxygen atoms. So basically, like you can see in the tetrahedra here, there's 4 oxygen atoms surrounding a silicon or aluminum atom. And in the octahedra, there's 6 oxygen atoms surrounding a center aluminum, magnesium, or iron atom. And these oxygen atoms will be shared at the edges of the tetrahedra and the octahedra in between those two layers. The layered nature of clay minerals or phyllosilicate clay minerals makes them layered in their, macro structure as well as, their microstructure. So we can actually see that they have a very platy nature. And the reason for that is because their structure is literally plates or layers of atomic arrangements. And so they break along those layers because that's where they would naturally break. And so that's why they're just very platy. And clays can be characterized and classified into groups based on the ratio of tetrahedral to octahedral layers. For example, moderately weathered soils typically are dominated with 2-to-1 ratio clays, such as montmorillonite and illite, which are in the mica group. As you can see here, these are 2-to-1 ratio of silica to aluminous layers, or basically tetrahedral to octahedral layers. And you can see in some cases they have interlayer charges that require, in this case, potassium, which has a positive charge, to balance that out in the interlayer and kind of fill that interlayer. And then for strongly weathered soils, these are dominated by kaolinite, as shown on the top here in green, with a 1-to-1 ratio of tetrahedral to octahedral layers. And this is due to greater silica loss because these soils are weathered more strongly. So what this means is basically your mica or illite group has a 2-to-1 ratio of silica rich to non-silica rich layers because more silica is available because it hasn't been dissolved away or weathered away due to strong weathering. It's only been moderately weathered. Whereas your 1-to-1 ratio kaolinite type clays have less silica available because they've been more strongly weathered, and so they have to have a 1-to-1 ratio of silica layers and other cation octahedral layers. And then, like I already mentioned, depending on the composition, some of these layers, whether the tetrahedral or the octahedral layers, might have a net negative charge, which then can be balanced by interlayer cations, such as sodium or potassium, which are positively charged to balance out the negative charge. And then sometimes interlayers can contain water. And all of these clay phases, all of these types of phyllosilicate clays, incorporate nutrients that are important for life, including potassium, magnesium, iron, nitrogen. All of these nutrients they incorporate into their structures, so sometimes they can limit nutrient bioavailability. Just an interesting anecdote really quick I found as I researched for this video is that clay minerals have been found on Mars in rock collected by the Curiosity rover. Basically, the rover drilled into rock near Gale Crater, or in Gale Crater, I guess, on Mars, and it was analyzed by the instruments on the rover, and basically they were able to conclude that it was very similar to the layered phyllosilicate, aluminosilicate type clays that we have here on Earth, which is really significant because it means that it had to have formed in contact with water, and it may even retain some water in its structure, like we just talked about with the interlayer water and cations that can be in the interlayers. So that's really interesting and cool. But moving on now to the second major type of clays that we've talked about, and these are the oxides. So recall from the first clay video that we talked about how aluminosilicates can form and be kind of left behind as secondary phases due to weathering in soils, but so can oxides like iron and manganese oxides. Again, these are not silicates. They do not contain silica groups in their formula. They just contain iron or manganese plus oxygen, so they're just oxides, but they can still be layered very similarly to phyllosilicates. So here, for example, we can see the pinkish purple manganese oxide octahedra layers in this manganese oxide mineral, and then you have interlayers just like with the other clay minerals I showed that may be filled with potassium or other cations, or even water, depending on the charge of the layers. But the only difference in this case between this structure and the structures I showed previously is there's no silica tetrahedra layers, there's just the octahedral layers with the manganese oxide. And down below this picture, this is just a picture showing manganese oxide nodules that have precipitated at the bottom of the seafloor. And there are many different structures of both iron and manganese oxides. Here is some SEM or scanning electron microscope images of some different manganese oxide structures. Again, even though they're different than the phyllosilicate clay minerals, they are also very platy in their crystal habit because most of them are layered. But manganese oxides can also be what we call tunnel structured. So instead of phyllomanganetes or layered manganese oxides, there's also tectomanganates, which are tunnel structured manganese oxides. So they have kind of like these tunnels of manganese oxide octahedra rather than layers of manganese oxide octahedra, but I won't get into that. That's just cool to me. And then iron oxides also form a variety of structures. Again, iron oxide is just rust, basically, but there are many different minerals of iron oxide that can form depending on the starting material. Obviously, if you're getting iron that's rusting, it's probably elemental iron that rusts, but you can also have ferrous iron that becomes oxidized to ferric iron that forms a variety of different minerals. But again, the simple building block of all of these mineral structures is again just an oxide octahedra. In this case, it's an iron oxide octahedra. So iron at the center with 6 oxygen atoms surrounding it, just like the manganese oxide octahedra. And oxides and hydroxides often form from straight oxidation of solid phase reduced iron or reduced manganese. When I say reduced, I just mean that it has an abundance of electrons. Oxidized, or the process of oxidation, is the taking away of those electrons. So basically your iron here, the silver part, has an abundance of electrons. Then the red part here has given those electrons to oxygen and become oxidized, basically, in the simplest of terms. And it just changes its formula. That's why it changes. So it can form via oxidation of, solid phase iron, such as the rusting here. But it can also be, in extreme cases, be dissolved as an ion. Ferric iron can be dissolved as an ion in very low pH acidic solutions and then precipitate directly out of solution if it becomes saturated or if pH rises. Same thing is true for manganese oxides. They typically form via oxidation and or direct precipitation from solution, depending on saturation state, pH, redox conditions, reducing and oxidizing conditions, all of these things. But that gets into very chemistry-y things. So the general gist of it is when iron rusts or oxidizes, the red mineral that forms is iron oxide. And the process of this is just reduced iron or iron with an abundance of electrons, giving away one or more electrons to form ferric or oxidized iron, or iron 3, that then reacts with and forms iron oxide or iron hydroxide, depending on whether it's hydrated or not. And the same process goes for manganese oxides. And one question you might be wondering is who gets the electron? Well, it's always the oxygen in the case of forming oxides, but there can also be other electron acceptors. Actually, this is supposed to be iron 3, not 2, so sorry about that. But the point here is that anything that has that's oxidized or has a lack of electrons that is out there to go get some more electrons, like sulfate or ferric iron or oxygen, those can all be the electron acceptor or who the electron is given to in this process. But in general, it's oxygen, just molecular oxygen, that oxidizes these things. And at room temperature, rusting or oxidation of iron requires water. So this is typically something that's in an aquatic environment, or at least something that's wet. But sometimes at really high temperatures, you can get, rusting and oxidation that doesn't require water. But I think that's not typical for natural environments. And the ends in these formulas here, these chemical formulas, depend on how oxidized the iron or manganese becomes. For example, sometimes you can have a mixture of both iron 2 and 3 in an iron oxide formula. And so that will change the amount of oxygens that are required to balance out that compound, the charges in it. It also depends on temperature and pressure conditions, as well as whether it's an aqueous reaction with aqueous ions or whether there are solid materials that are becoming oxidized. And so that also can change the degree of oxidation that occurs and how the reaction happens. And also whether the reaction is biologically mediated, in other words, whether it's bioinduced or biocontrolled, or whether it's completely abiotic. So bioinduced and biocontrolled are things I talk about in my biomineralization videos, but basically what these terms mean is in bioinduced scenarios, there is a passive mediation of the oxidation process through biological processes. For example, biological organisms that are producing oxygen, like photosynthesizers or something, might then cause iron to become oxidized that is in the vicinity because there's oxygen around. And that is more of an induction process rather than a controlling process in terms of the organism's role, because it's more of a passive role than an active role. Whereas in a biocontrolled scenario, you have things like microbes that literally take up reduced iron and they use it in their metabolism and literally oxidize it as their metabolism, and then they, poop out the ferric iron or the oxidized iron. Same thing with manganese. There's tons of manganese oxidizing bacteria out there. Manganese oxidizing bacteria are actually responsible, I think, for the majority of manganese oxides that form in the environment. So they play a huge role. If you want to check out more about iron oxidation specifically and how iron oxides can form from, for example, sulfide minerals, I talk a lot more about that in my microbial corrosion video as well as my bioleaching video. So I will link the bioleaching one up to the top because that kind of comes before the corrosion one, but you can watch those to learn more about this process at the bottom here. I kind of walk through this step by step in those videos. And lastly, we have the classification of common clay minerals. So the common clay minerals, like we talked about, include phyllosilicates, which is the family of common clay minerals. In this case, the first one we're going over is the group kaolin, which includes minerals such as kaolinite, as well as polymorphs or different structures of the same composition of kaolinite. And again, this is a 1-to-1 layer ratio of silica tetrahedra to aluminum octahedra. And again, the composition is aluminum silicate. And then we have the smectite group, which is again a phyllosilicate, but the smectite group has a 2-to-1 ratio of silica tetrahedra to other cation octahedra. These other cations can be things like calcium, sodium, aluminum, magnesium, iron, depending on the primary mineral and all of the other things we've talked about. And the minerals that can have a variety of this, composition here include montmorillonite, nontronite, beetalite, and saponite. And this smectite group is the same type of clay found by Curiosity on Mars. And then we have the illite group, which for some reason people decided to put illite, which is a mineral and a group, in its own group. I don't know why, because it is still 2-to-1 in its silica tetrahedra to octahedral layer ratio, just like the smectite group. But for some reason, they isolated illite. Poor illite. But it has a slightly different composition, but again, can range quite widely with various amounts of potassium, magnesium, aluminum, iron, etc. And then we have chlorite, which again is a phyllosilicate and has a 2-to-2 ratio of silica tetrahedral layer to other ion octahedral layers. And that is sometimes also listed as 2-to-1 because the octahedral layers can differ in their composition. And so these minerals include chlorite variations, which are amosite, camosite, cookite, and nimite. And these are listed 1-through-4 here and have various compositions with more kind of enrichments in ferromagnesian minerals or iron and magnesium rich components because chlorite comes from a more mafic primary mineral composition typically. And lastly, we have oxides and hydroxides, including the iron manganese oxides we talked about in the last few slides. Again, these are not phyllosilicates. They are sometimes phyllo or layered, but they're not silicates. They are oxides in terms of composition. So they don't have a layer ratio classification because they don't have silica tetrahedra layers. They only have their manganese oxide octahedral layers as well as iron octahedral layers. And sometimes they're not even layered. Sometimes they're blocky or tunnely or whatever. And Iron oxides can include things like hematite, iron 203, ferrihydrite, iron 203 with water, aka hydrated, goethite, which is an iron oxyhydroxide, and then manganese oxides or common manganese oxides include pyrolusite, manganese O2, and bernasite, the hydrated manganese oxide. And there are, I think, like 40 other types of manganese oxides and iron oxides that I'm not listing because there's such a large variety, but you know, you can't list them all. So these are just some of the common ones, and I hope that you enjoyed learning about them as much as I did. I know clays seem like a boring topic, but seriously, they're so interesting. Anyway, if you guys want to check out the related clay videos, we have the first clay video that I did over what clay is, how it forms, and all of that over to the left here. And we have the clays and their role in the origin of life that will also pop up any second here if it's out by now. And if you want to check out any of the references I'm using to make this and other clay videos, you can check out my description box down below. And with that, guys, thank you guys so much for watching, and I'll see you in the next video. Bye!